Hi, welcome to ESI 412, Nanotechnology, Materials, Infrastructure, and Safety. I'm Professor Ukjun Nam at the Pennsylvania State University. So this is the outline of today's lecture. So I will talk about a little bit of the overview of that optical lithography, and then we'll talk about the exposure system, and then some parameters and photoresist. And then we will talk about the lift-off process, and then we will also talking about the EUV lithography and then X-ray lithography. So, what is the good lithography? No matter what kind of technology you are using, including optical lithography, there are also advanced lithography like e-beam lithography or nano imprinting. No matter what kind of techniques you are using, when people talking about a good lithography, those kind of lithography techniques should offer a high resolution and then precise alignment accuracy, and then throughput is one of the factors to apply those kind of technologies for a commercial production. And why people are what's the kind of reason for those kind of microchip, microelectronic industries likes to use optical lithography for their production line? The major reason for that is this optical lithography is reliable, and then it is reproducible, and then it offers high throughput. So the high throughput here is at the wafer size. At the generation right now, people are using 12-inch wafer size. People wanted to process more than 100 wafers per hour. So that's the kind of a throughput. But as people, those kind of dimensions getting smaller and smaller, those kind of exposure tool price is kind of getting higher. So for the current technologies, if people include all those kind of accessories, one exposure tool easily costs $100 million. So it is kind of expensive to make a photo mask, and then exposure tool is kind of also very expensive. So that is why this kind of lithography process takes more than 35% of the cost to produce those kind of microelectronic chips. And then the development of this kind of technology is kind of getting more complex, because to go to the next generation lithography technology, people also should develop new equipment and then new resist. So all different kind of areas should move together. So the development of this kind of technology is getting more expensive. So it's kind of very interesting to see this roadmap from the International Technology Roadmap for Semiconductors. So it's kind of published in 2007. But it is kind of interesting to see the predictions of this kind of a technology about a couple years ago. At the time, the semiconductor industries, they are making about 65 nanometer feature size of the devices. And then they just predicted for the next feature size, which is a 45 nanometer, people just expected to use the current 193 nanometer wavelengths of the exposure tool. But from 32, people just expected some kind of a new lithography techniques should be applied to use this kind of 32 or smaller feature size. But right now, using this kind of same technology, 193 nanometer with an immersion lithography, we are right now 22 nanometers. And then in laboratories, people can make smaller than 20 nanometers. So it's kind of interesting to see what happens to use this kind of technologies still for this kind of 22 nanometer device fabrication. So let's briefly talk about exposure system. So this is a typical exposure system for the optical lithography. So there are three kinds of the exposure tool. One is a contact, and then proximity, and then projection. This contact and proximity lithography can be done using one single tool. The only differences between contact and proximity lithography is this is a photo mask. So in this case of that, the photo mask directly contact with the substrate coated by the photoresist. And then proximity effect, we have some spacing between the photo mask and then this photoresist coated substrate. Projection type is the device we are using for the commercial production. So we call that this type of the exposure tool like a projection scanner or projection printer. So this is the kind of example of the pictures for those kind of a contact and proximity exposure system. And then the contact lithography, it has a light source, and then there is some kind of optical systems, and then there is some kind of a shutter, so you can control those kind of exposure. And then, as I said, the photo mask directly contact the photoresist coated substrate. So for the contact lithography, people use the same size of the photo mask with the substrate. So one-time exposure will cover an entire wafer. In a sense, it is fast and simple and inexpensive. And since this kind of photo mask directly contact the substrate, it offers relatively good resolution. But this kind of a contact of the mask to the substrate potentially cause some damages or contamination on the mask. So that's the drawback of this kind of an exposure tool. Proximity lithography, the same kind of configuration of the device tool, but there is a little bit of the gap. So this gap between photomask and then substrate reduce the damage and contamination on the photomask, but this gap just make the diffraction effect much bigger. So its kind of a resolution is kind of relatively bad, and it also using the same size of the photomask and then substrate, so it only need one exposure, so it has the same kind of advantage those kind of contact lithography has. And then both contact lithography and then proximity lithography, it does not use any lenses, so the pattern transfer ratio is 1:1. In other words, if you have a 1 micrometer feature size on your photomask, those kind of transferred pattern also is 1 micrometer. Projection type exposure tool is kind of a little bit different. In other words, we call that as a stepper. So this is the kind of example of the picture. So this is a stepper, and then this is the computer controlling all those kind of exposure process. So it has a light source, and then optical systems, and then this is a photomask, but its kind of a shape is kind of very similar to photomask, but somehow the people using this kind of projection lithography, people call this same kind of a photomask as a reticle. And then it has lenses. So normally the feature size on the reticle reduced about 4 to 10 times smaller to your photoresist. So technically this radical is kind of separated from the photoresist coated substrate. So like proximity lithography, we don't have mask damage or contamination. And then since it uses lenses, so it offers excellent resolution. But since it uses lenses and some other kind of optical, some other optics, so the tool price itself is kind of much more expensive than contact lithography or proximity lithography exposure tool. So in ideal system, what's happening is, let's say this is your photo mask, and then this is the quartz plate, and then this black thing is on chromium. So in ideal system, if we have this kind of a photo mask, and then if we apply the light from this side, this kind of shaded area should have 0% of the intensity, and then this kind of transparent exposed area should have 100% intensity of the light, and then this interface between shaded and then clear area should have a very sharp intensity differences. So from 0 to 100. But as as Professor Fonesh covered in the previous lectures, we do have diffraction. And those kind of diffraction effect is getting severe, getting more and more important as those kind of feature size we are using is closer to the wavelength we are using or smaller. So in reality, all this kind of an exposure intensity not turning out to be this kind of a very sharp rectangular shape. In ideal system, this is the one part in an exposure tool. This is the resist. So when we apply the light using the same kind of photo mask, those kind of shaded area, let's say this is a positive resist. So those kind of exposed area should be removed after development process, and then not exposed area should remaining perfectly, and then this kind of interface between exposed and then unexposed area should be very steep, and then very almost 90 degree of the profiles between these kind of two areas. But in reality, this kind of profiles is not this kind of perpendicular, but has some kind of a distribution. We will talk about this. This is all about the photoresist contrast. So we will talk about this in the later of the slide. So this is the ideal case, but in reality, none of the side exposure tool is not perfect, and then the photoresist is not perfect as well. So that is why we always have some kind of an errors when we do the lithography. So as to the exposure tool side, we wanted to evaluate how good those kind of exposure tool is. So the modulation transfer function is the kind of a function evaluating how perfect those kind of exposure tool is. And then this is an ideal case when those kind of exposure tool is kind of a perfect. But because of those kind of a diffraction effect, the intensity at the wafer is not this square-like perfect intensity profile, but it has a more likely this kind of a curved distribution. So this is the one of the example. So in this case of that, those kind of unexposed area, the intensity is not 0, but it has a sum of the intensities. And then the maximum area, this is a shaded area, and then this is an exposed area. It has some kind of intensity. So we just, based on this kind of a minimum intensity and the maximum intensity, we can just calculate the number. So in this case of that, maximum is 5 and the minimum is 1. So this one is on about 67.67 is the MTF, modulation transfer function. This modulation transfer function, the maximum number can be 1, and as the number is kind of getting close to 1, the performance of your exposure tool is kind of getting closer to the ideal system. So let's talk about the optical lithography parameters. So the resolution is the one of the most important part in the lithography. So the resolution is determined by 3 parameters. That is on wavelengths of the light, and then numerical aperture, and then K1 constant. So this wavelengths of the light is kind of pretty straightforward. It is kind of directly related with the wavelength of your light source. And the numerical aperture is more likely related with the lenses you are using. And then this kind of a K1 factor is kind of the most complex parameters. And then this one can be obtained by the experimental factor. So the good resolution is a small number of R. So to achieve the small number of the R, the wavelength should be small. In another word, the wavelength of the light should be shorter. And then the numerical aperture should be big. And then the K1 constant should be smaller. So making this kind of a trend is the key to minimize, to improve the resolution.
So where does kappa actually come from? The K1?
We will go through about this, but this one is more likely achieved by the experimental section. So what kind of experimental can improve these K1 factors, we will talk about this in the later slide. And one of the conflict parameters is depth of focus. So depth of focus is some kind of range you can maintaining some kind of reasonable resolution. So it uses the same kind of parameters, wavelengths, numerical aperture, and then experimental constant. And then the DOF, the good depth of focus, is the big number. So to achieve the good depth of focus, we should have a longer wavelength, smaller numerical aperture, and then big K2 constant. So these 2 parameters, resolution and then depth of focus, it is kind of pointing opposite direction. So working with just satisfying all these kind of 2 factors are controversial. So let's talk about resolution first. So as I said, the working with the wavelengths is the most straightforward. So just simply changing the light source, which wavelength is kind of shorter and shorter, you can just keep improving the resolution. So that is why people just moved from UV2 all the way down to EUV, and then also started to looking for the potential to use X-ray, which wavelength is around 1 nanometer or smaller. So this is the Mercury lamp. So Mercury lamp, if we are using a proper filter, we can make this wavelength of the light, this wavelength of the light, and this wavelength of the light. So instead of we are just mentioning about this specific number, since this kind of wavelengths is so important, people just call that as a G-line spectrum or I-line spectrum. And then this kind of I-line spectrum is used for the most of the contact or proximity lithography. So using this kind of wavelengths, people can achieve around 1 nanometer or 1 micrometer of the feature size. And then to go down to the micrometer, we need to use a much shorter wavelength. And then from that point, people started to use this excimer laser. So up to this point, we used to use a Mercury lamp. So from lamp 2, we started to using a laser. So next from the I line is the KRF laser, which wavelength is on 248 nanometer. And then right now we are using ARF laser, which provide 193 nanometer in wavelength. The requirement of the light source is, as we discussed about that, to have the good resolution, the wavelength should be shorter. So we need a short wavelength. And then we should have a high intensity of the power density, because those equal power density multiplied by the exposure time. So if we have a high power density, we only need a very short exposure time. So high density is directly connected to a much less exposure time. In another word, a much faster processing time, higher throughput. And then this light should be stable. So improvement of the NA, the numerical aperture, we can just increase the diameter of the lens. So if we increase the diameter of the lens, what kind of advantage we will have? As we can see, if we have a much bigger diameter of the lens, there we can collect high order diffracted light as well. So if we have this kind of diffracted light, if our kind of a lens diameter is about this, we will lose all this kind of a high order diffracted light. So that is why we cannot achieve a pretty good resolution. And then the bigger lens is another way we can choose to improve the numerical aperture. One is just to try to make the lens surface as smooth as possible, so we can reduce the aberration effect by those kind of surface roughness. The third thing we can do is we can put some materials which dielectric constant is bigger than 1. So in another word, we call that kind of technology as an immersion lithography. So that could be another way we can increase the numerical aperture. If we have some materials which dielectric constant is kind of bigger than 1, when the light coming in, after passing the light, the degree of the bending of the light is kind of much lower than air. So that's the one of the reason why we are using the immersion lithography. So we talked about resolution and then depth of focus, just pointing different direction. One of the way.
So what is immersion lithography? Just like put the water between your photoresist?
Yeah, we will talk about that in the later slide. Yeah, so since these two parameters kind of pointing opposite way, one of the way we can just compensate those kind of two controversial direction is if we are using chemical mechanical policing, we can just make the focal plane to be as flat as possible. So if we have this kind of a structure, and then if we have a film deposition, we will have this kind of a rough surface. And if we need to do the next lithography, this is a photoresist. If then this point and this point has a different kind of depth of focus. If we use this kind of a chemical mechanical policing and then make that structures to be flat, if then under the same kind of a condition, we don't have this kind of a differences in depth of focus. So using that way, we can just reduce those kind of controversies between resolution and then depth of focus. Immersion lithography is something like that. So up to the technology by 193 nanometer, people are just remaining between this imaging plane and then a final lens with an air. And when we have an air between this final lens and then the imaging plane, when the light comes in, the degree of the bending is kind of much bigger. So that is why some of the light just reflected back and never be able to reach the substrate. And then some of the light, there are kind of much fewer light can be collected to the imaging plane. So if we have this kind of materials, which dielectric constant is kind of bigger than 1, actually the air has the lowest dielectric constant. If then a degree of this kind of light bending is kind of much lower than this case. So that is why even for this kind of light, normally the light at this kind of edges has the high order of the diffraction. So we can have more high order diffracted light to the substrate. So just putting this kind of liquid solutions between this kind of final lens and then substrate, we have the same effect having much bigger lenses. Actually, using the bigger diameter of the lenses, the major purpose is to collect this kind of a high order diffracted light, right? So using this kind of a liquid, we can have the same kind of effect. The reason why those kind of exposure tool is kind of getting more expensive is because to improve this kind of numerical aperture, people started to use bigger and bigger diameter of the lenses. So for the high performance exposure tools, those kind of tools are getting heavier and then much more complex because of this kind of much bigger size of the lenses. And that's the one of the factor increasing the price of that exposure tool. So so those kind of improving those kind of wavelength and then numerical aperture, we can use such a immersion lithography or those kind of bigger kind of lenses or things like that. So how we can improve those kind of K1 factor, which can be done by the experimental side. So one is on up-axis illumination. So in normal case, we apply the light perpendicularly like this. So in this case of that, this kind of a zero order diffracted light just dominate when it landed to the imaging plane. But as you can see, this is the kind of a simulation result. As the order of the deflected light getting higher, this is the zero order of the reflected light. It has just one single pattern. As the order of the deflected light is kind of getting higher, it is kind of much closer to our ideal shape. So that is why people wanted to have this kind of a high order diffracted light just to the imaging plane. So we wanted to remove this kind of a zero reflected order of the light because this one has the highest intensity. So if this one just landed to the imaging plane at the same time with this kind of a high order deflected light, this zero deflected light will be dominant. So by tilting the angle, we can just only have those kind of a high order diffracted light to the substrate. So using that way, we can increase those kind of resolution. Second thing is we can use a phase shifting mask. So phase shifting mask is if we have this kind of a photo mask, actually this chromium layer should position toward to the substrate side. So if we have two openings, and then if those kind of spacing is kind of too close, we will have this kind of two independent intensity of the light at the imaging plane. If these two light are in the same phase, this kind of a middle area, those kind of a light intensity will be added up. So if we just somehow depositing some metals or etch away a little bit in this area, so if we can change the phase of the light coming to the photo mask, if then this area, since the phase is kind of an opposite, so that is why it just destruct each other, cancel each other, so we have a very good resolution between these two openings. So to achieve this kind of discrete patterns, using the phase shift mask is another way we can use. The third one is we can working with optical proximity correction. So if we wanted to achieve this kind of L-shaped pattern, if we just make the openings in the photo mask like this kind of an L, if then this area has a little bit more kind of a light densities than other areas, so it turns out to be we will lose these sharp edges to be more rounded, and then these edges we do not have much intensity, so this edge also will be rounded. So in this case of that, if we just remove some of this kind of an area and then just add up some of these kind of sub-wavelength features, if then we can have much closer L shape, and this is what we can achieve. Actually, this kind of optical proximity correction is normally happening before you are making your photo mask. At that stages, you are designing your patterns using the software, like an L-edit or those kind of software. And then using the numerical analysis, you can just apply the light, and then based on those kind of electromagnetic field, you can expect if those kind of a distribution of the light intensity is kind of a closer to what you want to achieve. Another thing is we can add a couple more kind of process steps to achieve smaller feature size. So you can add, instead of doing one lithography, you can do the lithography etch, or lithography freezing, lithography etch, or those kind of a more complex kind of a process will reduce the feature size you can achieve. So I'm not gonna follow all these, but I will give you one example how people are using this kind of additional process to achieve much smaller feature size. So let's say this much of line width is the maximum line width. In other words, smallest kind of width you can get under your kind of exposure tool. If then for the first lithography, we have this kind of pattern. And since this is the highest resolution we can achieve, we cannot go much smaller, but let's say this is the kind of feature size you want to achieve. In this case of that, you conformally coat one film like this, and then if you do that, there is this film can be deposited vertically or laterally as well. So this area, the thickness of the layer is kind of much thicker than this area and this area. So after film deposition, if you do the blank etch, since this area, the film thickness is thicker than this area and this area, so this area, the film will be remaining. And then at this point, you will remove this green photoresist. And then using this blue structure as a hard mask, you will etch it further to the materials you want to etch. And then after the etching process, if you are removing this blue material, this is the kind of a structure we can achieve. So based on the film thickness and then this kind of etching condition which involved in the etch selectivities between this gray and then blue area, you can achieve much smaller feature size which cannot be achieved by your exposure tool. So that is why people have this kind of process or some other kind of much more complex way to achieve these kind of small patterns.
Like the nail rod, if you are going to make the really small diameter nail rod.
That's possible, yes. So let's talk about the photoresist. So photoresist, what is a good photoresist? It should offer high resolution and then high etch resistance. So some of the application we are using for the lithography is, and after do the patterning, after the lithography process, we want to do the etching of the material underneath of the pattern. In this case of that, we want to have this kind of a photoresist has the highest resistance to whatever etching step. Could be a plasma or wet etching. And then this resist material should have a good adhesion with the substrate. In the previous lectures, we are talking about this kind of high aspect ratio of the resist pattern for the nanoscale structural fabrication. In this case of that, actually good adhesion is kind of getting more and more important as your feature size is getting smaller and smaller, unless this kind of a high aspect ratio of your patterns will easily fall down, even not with for this kind of adhesion only, but also those kind of capillary force while you are drawing this kind of patterns during the lithography development process. And then it also, when you have some kind of very rough, this kind of feature size due to the kind of add processings, it should have a pretty conformal coatings. That's one of the requirement. And then it should have a good contrast and then sensitivity. We will talk about this in the later slide. And this is a little bit opposite to number 2. So we want this photoresist is as strong as possible during the following process. But once those kind of following process is ended, we want to remove this kind of photoresist as easy as possible. So that's the one of the requirement we want to have. So what kind of a component make photoresist? So we have solvent, and then we have a resin, and then we have a photoactive molecules. So this kind of a solvent control the thickness of the resist. So when you are spin coating, depends on the spin speed, your film thickness is kind of getting thinner. If you dilute your standard resist with some kind of a solvent, under the same kind of spin speed conditions, your resist is getting much thinner than non-diluted resist. The resin is the material remaining on the substrate after finished all those kind of processes, and then this kind of photoactive molecules cause those kind of removal and then cross-linked after the UV exposure. So for the positive and negative tone photoresist, in a kind of a simple kind of a term, positive resist, the resist are remained. So those kind of when UV light, resist is kind of exposed under the UV light. If the resist is removed, those kind of exposed area is removed, we call that kind of a resist as a positive photoresist. And then if those kind of UV exposed area, the photoresist is remained, we call that as a negative photoresist. So photoresist, no matter what that is, positive or negative, it has a sensitivity. So sensitivity is an basic energy to make those kind of photo reaction is happening. So for the positive resist, there is a certain energy to remove, to cut all those kind of cross-linked of the polymers. So this is the energy needed to those kind of reaction is kind of completed. So as this kind of dose is kind of smaller and smaller, we call that that kind of resist has a good sensitivity. The contrast is as we just reviewed in the ideal case, when we have a shaded area and then exposed area, in the ideal case it should have this kind of a steep interface between this kind of exposed and then unexposed area if this is a positive photoresist. But in reality, this kind of a photoresist is not perfect. So even for this kind of example, around 40% of the dose, this kind of a photoresist started to dissolve. And then, of course, if it is kind of exposed under the 100%, so between 40 to 100% of the exposure intensity, power density, those kind of resist started to dissolve. So that is why we have this kind of a slope. So in ideal case, this this intensity, this one and this one is getting kind of a closer, and then this sensitivity is kind of getting lower. So that is the kind of ideal. If we meet these kind of conditions, then it will getting closer to the ideal case we just reviewed. So photoresist, this is the one of the example of the photoresist. So normally has an noble-like resin and then some kind of a photoactive compound. So this is the resin. So when this P-type photoresist exposed under the UV light, it just lose nitrogen bond, and this bond is replaced by this carbon and oxygen bond, which is soluble to the water. So using this kind of reaction is happening by the UV exposure, and then after replacing this kind of element, those kind of polymers will be dissolved into the following development process. So when those kind of water molecules see this kind of carbon and oxygen, it just make this kind of molecules, and then it can be removed. Negative resist, upon it is kind of coated on substrate, it is just a monomer. When it is exposed under the UV light, this kind of high energetic light make those kind of photo element activated, and then those kind of photo element just to make these kind of monomers cross-linked each other. So this kind of UV exposed area, after the development, those kind of UV exposed area will be remained. There are chemically amplified photoresist. The major difference is actually this kind of chemically amplified resist is available both P-type and N-type. This specific resist has some kind of a molecule called as a photoacid generator. So these molecules, upon exposed by the UV light, it just produce some acid, and this acid cut those kind of a cross link under the polymer. So that causes the same effect. But this kind of a chemically amplified photoresist, since it uses this kind of acid production, so that is why it needs much shorter exposure time. And again, the shorter exposure time increase the process time, and then will increase the throughput of your process. So that is why this kind of chemically amplified photoresist are getting popular. For the photolithography process, the regular process is on substrate. You first spin coat your photoresist, and then soft bake. So during the soft baking process, you will remove additional solvent on your photoresist. And then you do the exposure. And then you can do another baking, or you can directly do the development. If you skip this post-exposure bake, actually this is the kind of a simulation result under the exposure condition. This is a photoresist. So those kind of wavelengths just causes these kind of standing waves. So if you just develop without post-exposure bake, you will have this kind of standing waves on the side wall of your photoresist. If you do the post-exposure bake, you will simply give more time, those kind of polymers rearranged. So you will have this kind of a smooth side wall, and then this is the conditions after do the post-exposure bake. Actually, these two are both the result after the post-exposure bake, but the lower temperature condition does not work very well compared with a little bit higher temperature bake. But this kind of a right condition of the post-exposure bake make this kind of a side wall much flat. So lift-up process. The lift-up process is making this kind of undercut structures. And then the lift-up process needs some special resist called as a lift-up resist. So the lift-up resist should be thermally stable and chemically stable, and also should have a good adhesion. Because if this is a substrate, those kind of lift-up resist always kind of coated first. And then after that, you need to coat another resist layer. We call that as an imaging resist. Lift-up resist in most of the cases is not photosensitive, but your imaging resist does. So what happens is after this, after coating the imaging resist, we need to do the soft bake. If the lift-up resist is not thermally stable, during the soft baking process, these two resist layers can be mixed up, which we don't like. When this kind of imaging resist is applied for a spin coating onto the lift-up resist, it is applied as a liquid form. So if somehow this lift-up resist is not stable for the solvent used for the imaging resist, and then make some kind of a reaction, if then it will also make some kind of a mixture between these kind of two layers. That's what we don't like. So in a sense, we want this resist should be thermally and chemically stable, and then also should have a good adhesion. Then why do we need this kind of undercut? So if we don't have an undercut after lithography, the lift-up process is we first define patterns using the photoresist and then do the metal deposition. If we don't have an undercut using just a single photoresist, those kind of layers deposited on the photoresist are all connected. So when we want to remove all this kind of an area during the following removal processing, since all these kind of layers are connected to each other, so during this kind of removal process, there is some kind of competing forces. One is the adhesion of these kind of materials on the substrate, and then the strength of the film. So ideally, we want to have those kind of a cut happening here and here, but depends on those kind of a competition of the two forces. Sometimes those kind of breakage happening here and here, and then this kind of additional film remained after completed these kind of structures. If we have an undercut using the lift-up resist, this kind of films deposited is not continuous. So we don't have those kind of competing reactions, and then we do have this kind of very smooth edges. So this is one of the example of this kind of a single resist case, and then this is another example when we use the double layers with the good undercut. Why this kind of structures, vertical structures called the rabbit ear is the problem. If we want to, let's say, if our kind of next structure is on kind of a depositing insulator, and then we want to deposit another metal layer. If we have a very smooth kind of edges, it does not have any problem. If we have this kind of vertical structures remaining, if then depends on the method you are using for this kind of insulator material deposition, it cannot kind of conformally coating this kind of vertical structures. And then when you put another kind of a metal layer on top, this one metal layer and then another metal layer can be easily short. So it can just make some kind of a defect on your device.
So if you just deposit the electrodes and we are not going to put any oxide layer, they should be okay. If we just measure the source and drain and without any additional deposition.
Right. So depends on yeah. Right. So if you are using this kind of structures for hard mask, those kind of problem is kind of much less, but depends on how long this vertical structure would be. If this is a kind of a nanostructure, let's say you want to have achieve this kind of a dot pattern. If this kind of a vertical structure is kind of too long, instead of this kind of a clean round dot, you will have some part of those kind of metals can remaining, and you will have this kind of structures looking from the top. So this is also you do not want to have. So this kind of lifter resist has been developed about 15 to 20 years ago. Before this kind of resist was developed, what people used was just a single resist. So spin coat a single photoresist and then soak those kind of photoresist, imaging resist under the solvent like chlorobenzene or toluene. So those kind of soaking process modify the surface of the photoresist. So those kind of modified surface of the imaging resist is kind of much harder than its kind of usual characteristics. So after exposure and then do the development, those kind of modified area is the dissolution rate is kind of much slower. So using that kind of different kind of characteristics of the single material, people can make this kind of a latch structure, but those kind of modification of the surface is not that reproducible. So that is why this kind of a latch structure, this is also very thin, so sometimes easily collapsed, and then by the stress of those kind of modification, that can cause some kind of cracks as well. So using this kind of a dedicated lifter process increase the reproducibility and then yield as well. This kind of a lifter process is kind of getting more important, and then as we go through more kind of advanced lithography, which will kind of making smaller than 100 nanometer, we will talk a little bit more about this process during the later lectures as well. So when you do the lifter, you will normally see this is the image of the optical microlithography, optical microscope. So you will see always these kind of double lines. So the inner lines represent this interface, and then the outer line is this. So using this kind of optical microscope, if you want to do a little bit more undercut, you should use a lead filter, so you do not hurt this photosensitive layer. So if you just observe these things under the red light, and then if you do the further development, you can just keep increasing the undercut. So that's one of the techniques you can use. So right now, we are using 193 nanometer wavelength. But we don't know how small kind of a feature size we can go with the current technology. So extreme UV and then X-ray lithography is the next kind of a candidate, one of the candidates for the next generation lithography. So let's talk about the light source. So now we are sitting here, 193 nanometer. We even know what kind of a material can produce much shorter wavelength. So by the current trend, the next candidate is supposed to be a fluorine-based excimer laser, which will produce 157 nanometer in wavelength. But somehow, people just jumped all the way down to 13.5 nanometer, which is an extreme UV. Why? People just worked with this kind of 157 nanometer wavelengths of the light source. But the thing is, from this kind of a wavelength, this kind of a short wavelength is kind of too absorptive to any kind of a material. So it can just, the lenses absorb the light, photomask also absorb the light, and there is a pellicle. Pellicle is an, we said those kind of a commercial version of the photomask. Radical is kind of pretty expensive, so that is why in industry people coat very thin transparent layers on top of this kind of radical to protect this kind of radical from the damages and contamination. And even those kind of transparent single layer also absorb those kind of light, which is a very short wavelength. So we are wasting a lot of light through this kind of optical systems. And then the resist is also another problem. So the resist designed for this kind of wavelengths are also too absorptive for a 157 nanometer or shorter wavelength. So people just thought about, no matter how much we put the effort to develop these technologies, this 157 nanometer technology will not go forever. In a couple of years, they should work for another kind of a wavelength, which is more absorptive than 157. So at this point, what people decide was people just decide light transmission. So from this point, people just thinking about we should use reflection. So the biggest differences between the current technology and then the EUV exposure tool is no more transmission for the EUV system. So there is a light source, and then there is a bunch of meters and then optical systems. So everything, even for the mask, no transmission at all. It only uses reflection. So that's the biggest differences. But this kind of a 13.5 nanometer in wavelength, even reflection is not easy. So those kind of meters also absorb the light. So what people started to use is a Bragg reflector. So this is an alternating layers, which is on high and low refractive index films. And then those kind of film thickness is the quarter wavelength thickness. So using this kind of spatial structures, people want to have a resonant reflectivity to have a quality mirror. So Bragg's reflector is a structure looks like this. So alternating structures with a high index layer and then low refractive index layer over and over again. How many layers? People normally use 50 pairs of the layers, and then molybdenum and then silicon is the most, they are the most studied materials for this application for targeting around 13 nanometer in wavelength, because our wavelength is a 13.5 nanometer. So experimentally, there is some kind of interdiffusion and then defect between those kind of layers, and all those kind of imperfection of those kind of layers, people just optimize the thickness of the molybdenum as 2.76, and then silicon as 4.14 nanometers. 50 pairs of those kind of alternating layers, people can achieve a little bit higher than 70% of the reflectivity. And then in experiment, it is kind of closer to the 68%. Still, we are losing about 30% of the light by this kind of a mirror. But still, this is pretty good. EUV mask. To make this kind of a mask, since we are using reflection, so that is why the starting material is on this kind of a Bragg reflector. So on Bragg reflector, using some of the material like an aluminum, chromium, tantalum, or tungsten, we use an E-beam lithography and then reactive ion etching. We just forming these kind of structures. One good news for that is still we can use some kind of optical systems, so we can still reduce the patterns on the mask with a 1:4 ratio. So if we want to achieve 1 micrometer feature size on your substrate, the feature size on your mask can be a 4 micrometer, 4 times bigger. So that's a good news. So using this kind of a way, the light hit this area or absorbed and then never reflected, and then the light hit these mirrors will be reflected. So using this way, EUV can achieve those kind of a small feature size. Still, the light source of the EUV technology is not stable. People are using some kind of a pulsed laser or laser-based plasma or just a plasma to make this kind of a short wavelengths of the light. And then the intensity of the light is not high enough. And then we also lose that kind of a light through the optical systems. So EUV resist should have a very high sensitivity. High sensitivity means what in photoresist? Need a low dose. So using the chemically amplified resist is essential. So we can just reduce the exposure time. It also needed to offer high resolution. But one of the drawbacks using the chemically amplified resist is it always has some kind of a rough edges. So we should use the chemically amplified resist to increase the sensitivity in photoresist. But this kind of edge roughness is another kind of problem we need to solve. 13.5 nanometer wavelength of the light is kind of a very energetic light. So when those kind of light kind of directly illuminated to the polymer layer, it just started to produce some kind of gaseous molecule. It started to degassing. So those kind of gas molecules can diffuse into the optical systems and then can deposit it on your mask and mirrors and those kind of optical systems. Those kind of contamination will reduce the lifetime of the exposure tool. So that's another kind of problems we need to solve to go to the EUV technique. X-ray lithography is a kind of a technology people just put a lot of kind of time because its wavelength is 1 nanometer or even shorter. So this is the kind of configuration of those kind of X-ray lithography tool. So there is a light source, and then here is a mask, and then this is your substrate. The problem of the X-ray lithography is X-ray penetrate majority of the material. So the contrast on your mask is happening based on the materials which has a high atomic number and low atomic number. So low atomic number material, those kind of X-ray can penetrate easily. Those kind of high atomic number materials like gold, tungsten, tantalum, it cannot penetrate. So those kind of a different kind of combination of the materials can make the contrast. But bad news is an X-ray does not refract. So when the kind of a X-ray just going in the air, when it passes through the some materials, it is not bending. So that is why the image ratio between mask and your substrate is a 1:1. It's kind of very tough. We wanted to use this kind of X-ray lithography to achieve smaller than 20 nanometer in feature size. So if you, for example, if you wanted to achieve 10 nanometer feature size, you should make the 10 nanometer feature size on your mask. So that's tough. Another problem is this kind of a low atomic number material, normally silicon or silicon carbide, it is a membrane. So we are talking about a 1:1 ratio. So if your wafer is an 8-inch wafer, your mask also should be a 1-inch mask. But those kind of membrane material, its thickness should be between 1 to 2 micrometer to have a good transmittance. And then those kind of high atomic number material, its thickness is about this. So just imagine how mechanically fragile your kind of a mask would be. You never be able to make the contact lithography because it will break your kind of very expensive mask. So we should have some kind of a gap between the substrate and the mask. But one bad news is that even though X-ray does not have a refraction, but it has a diffraction. So as you have more gaps between the substrate and the mask, your image quality is getting worse and worse. So it's kind of very hard to control those kind of things. So that's the kind of one of the biggest kind of problem. And then those kind of thin membrane with those kind of high atomic number of the patterns, it can cause some kind of mechanical stress because they are basically film. So those kind of film might have a stress. So those kind of internal stress or local stress can distort those kind of image transportation. So it has that kind of a problem. And then when X-ray hits the resist, what happens is an X-ray is kind of very energetic. So it produces lots of photoelectrons and then OJ electrons inside of the resist. Those kind of low energy electrons generated in the photoresist is kind of very effective interact with those kind of polymer material. So what happens is those kind of random scattering make your kind of exposed area bigger. Depends on those kind of contrast of the resist. So that's another kind of problem. The third problem is those kind of X-ray should be very well coherent, very highly coherent. So to making those kind of very highly coherent X-ray, what you need to have is this kind of a synchrotron radiation source. Actually, this is the synchrotron radiation source, and then this is the regular size of the building. So this is kind of pretty big. And then to construct this kind of a source, it only costs about $100 million, but it is not that expensive comparing those kind of exposure tool. We are paying for this kind of a current exposure tool. So we are affordable to pay this money. But the thing is, one source can connect a couple of the exposure equipment at the same time. That's a good news. But the thing is, if somehow this kind of a source is not working, all these kind of multiple exposure tools are down at the same time. If this is an individual tool, couple of the tool can be down, but still couple of the tools are still working. But if we have some problems with the source, it just totally kind of stop the production line. So that is another kind of a problem. So we are talking about the technology which can achieve 22 nanometer or that kind of range. We talked about EUV and X-ray lithography technology today, and next lectures we're gonna talk about other advanced lithography. So at this point, we don't know which technology will continue this Moore's law, and then we will keep talking about other kind of technology during the next lectures. Okay, thank you.